means that you can measure both of them to infinite accuracy simultaneously. You don't get any disturbance measuring one. You don't disturb the values of the other by measuring one, and vice versa. Okay. Now, another way of saying something similar is if your operator A commutes with the Hamiltonian, h hat, then the expectation value of that observable A, or A hat, is 0. Sorry, constant. So when you differentiate, you get 0. It's basically this. So if your observable A with the corresponding operator A hat, if it commutes with the Hamiltonian, so in other words the commutator is 0, therefore the expectation value, the average measured value of observable A will be constant. So if you differentiate the constant, you get nothing. Okay, that's what's being said here. Now another thing we did a few sessions back is if you have two observables that are compatible, we showed that they have common eigenfunctions. They have the same set of eigenfunctions. They may have different eigenvalues because they're talking about different quantities that you're measuring, different observables, but their eigenfunctions will be the same. They'll have the same eigenset, if you like, right? So and these, so if you have stationary states, what's that? A stationary state, that's an eigenstate you get, an eigenfunction you get for your Hamiltonian when your potential, your V, is not a function of time. Right? It's only a function of position. Okay, so if you have an observable that commutes with H, then the eigenstates of that observable, A, will be the stationary states, because they're the eigenstates of the Hamiltonian. Right? I'll try to tie that again. You have an observable A with the corresponding operator A hat, and let's say that A hat and the Hamiltonian H hat commute. Okay, and therefore A hat and Hamiltonian, H hat, they are compatible. The two observables, A and the energy, so E, they will have the same eigenstates, same set of eigenstates. Right? All right. So here's your observable energy, and you can label then this common eigenstate that's shared between observables E and A in the following kind of way. So say for a hydrogen atom where the angular momentum is conserved. Now why would that be? Well, let's say you take a hydrogen atom that's spherically symmetric in terms of its potential. It's V, so it's a function only of r, the distance from the nucleus to, let's say, the electron. Now, so that means that this potential V, and hence the Hamiltonian, does not depend on the two polar angles theta and phi. Does not depend on them, and therefore the operator A, whatever it is, in connection with the hydrogen atom, if it does not depend on the two polar angles theta and phi, it will commute with the Hamiltonian, and hence the values how do I put this? So that the eigenfunctions of A and E are the same, and therefore you can write those eigenfunctions in the sort of following way. These two letters here, L and M, they correspond to quantum numbers with angular momentum. But in this case, those particular states, their eigenfunctions, I should have had more calories. My brain's starting to fade. Okay, when for your two observables, energy and A, with corresponding operators, the energy operator, in other words the Hamiltonian, and your A hat, when they commute, then let's say the angular momentum components of your Hamiltonian don't exist, because for the hydrogen atom we're talking about, we have that it's spherically symmetric, and the wave function is let's say symmetric. Then the eigenstate that's in common for these two observables you can write in this form. N, well, that's just it's called the principal quantum number. It labels the energy. Now we've seen this N before when solving infinite square wells and that kind of thing, where N is the integer that labels which discrete quantized energy level you're talking about. And L and M, they do something similar, but they're quantized integer values corresponding to allowed angular momenta. But we haven't done this yet. We'll do this next chapter, and chapter 8. So the angular momentum. I better skip that, because I haven't studied in detail chapter 7 or 8 yet, and I'm scratching back quite a few years otherwise. So I'll just leave that and come on to chapter 7, chapter 8. All right. Well, that's so. Yeah, I'll stop there because it continues on, but you can't see it on the next in the next session. Right. So basically, what this is saying is, when you have two observables that are compatible, so the commutator of their corresponding operators is 0, then you can label their common eigenstates. If you have A hat and B hat for two observables, A and B, they'll have common eigenstates. Then you can write the common eigenstates in terms of the eigenvalues of the two observables. In this case, that would be like energy, and in this case, angular momenta. When in the symmetric case, I'm probably just confusing you. This will become clearer once we've done chapter 7, chapter 8. Okay, I'll stop there.